Okay, here is, oh, let's see, can you hear me? I think, let's make sure. Yeah, I think so. Okay, let's go back. Here we are, we're gonna do a quick example on Bernoulli and talk to you about why we're doing that. And hopefully this will help. I'll also post this in our OneNotes. So, okay. Bernoulli substitution. It's a substitution method. And let's see, it can be applied to first order nonlinear differential equations. And what it does is it's going to reduce the equation to a linear one that then you're able to use other methods that we've looked at. The form of equation you needs to look like this. So it's almost like a linear equation, except for this y sub n over on the right side. Now, if n equals 0 or n equals 1, you do not need the Bernoulli substitution. If n is 0, then on the right side, you don't have y sub n because it would be 1. And you could just use integrating factor or separation. Then you, let's see, if n is equal to 1, then actually, yeah, then you have to use separation. In either case, if n equals 0 or n equals 1, you don't need the Bernoulli substitution. If n is something else, then you use this as your substitution. U is equal to y to the 1 minus n. So let's solve this differential equation. Let's multiply it through the k. This is k times y minus ky squared. And then to put it in the form we need, dy dt minus ky is equal to negative ky squared. Here, n is equal to 2. So the substitution is u is equal to y to the 1 minus 2. That's y to the negative 1. Then the next thing you do is similar to a u substitution, you're going to take a derivative of u, but with respect to t. So let's take derivative of u with respect to t. That's going to be the derivative by t of y to the negative 1. And this is implicit differentiation. We're differentiating a y, but with respect to t, and you don't see a t. So it's negative 1 y to the negative 2 times the derivative by t of the inner function, which is y, dy dt. And how about we write this as negative 1 over y squared dy dt. That's what du dt is. Okay, then let's work through what we do next. So the next thing you do is you take this thing, negative 1 over y squared, and you're going to multiply it on this side of the equation, and you're going to multiply it on that side. So dy let's actually not rewrite it. Let's just do this. So the right side gets negative 1 over y squared. The left side also gets the negative 1 over y squared. And it is worth, that's a similar step to the integrating factor. Multiplying the integrating factor on both sides. Here we're multiplying that negative 1 over y squared on both sides. The integrating factor, oh, you want to say hi? I'm not on a screen, Andy, but you can say hi.
Okay, tell them the rest of it.
Well, they can hear you.
Hi.
That's Annie.
Wait, I don't want to call.
I'm recording.
Well, anyways, hi. This was in the past, but hi.
What do you mean in the past?
Like, they're watching it after it happened.
Yeah, true. When they watch this, you and I will have already talked.
Have a good day.
Have a good day. Okay, go.
Good day.
On the left, you want to multiply this in. This is Let's see. -1 over y squared dy dt plus k and times 1 over y. Then we'd have equals, and on the right, everything cancels but the k, which is helpful. And now this is going to be a linear equation, you'll see. So this piece is all of this. Let me go back to, that's what I'm saying. So -1 over y squared dy dt turns out to be a du dt, and it will work that way every time. So that piece becomes du dt plus k, then the 1 over y, that is y to the -1, that's our u. So this piece becomes the u, and then the right side is k. And so now what we've made is, this is a first order still. It's linear now. It was nonlinear up here. But yeah, so this was first order nonlinear because of the 2, the y terms not appearing linearly. And incidentally, well, okay, we'll come back to that. This first order nonlinear, it is separable. So you could use separation of variables, but it would require partial fraction decomposition, and maybe you'd want to avoid that. Maybe try that out, see what you get. But here we've taken a first order nonlinear differential equation, used Bernoulli substitution, and we have now a first order linear differential equation. So now you're back to using either separation of variables, if you can do that, or integrating factor, if you want to do that. You have either option. So let's use integrating factor. We did mu of t would be e to the integral of k dt, and we're picking k because it's the coefficient on the dependent variable term. That's e to the kt. The left-hand side of the equation will become integrating factor times dependent variable, which is a u, equals the integral of the integrating factor times the right-hand side dt. Then let's see, I want to move this over a little bit. Okay, so now let's move forward. We would get e to the kt times u is, let's see, anti-differentiate. K is a constant. We'd have e to the kt, divide by the derivative of that exponent plus a c. So u is going to be 1 plus, here, let me back up. Now if we divide both sides by e to the kt, that's what we're doing. Then the left side becomes a u, the right side is e to the kt over e to the kt, that's a 1. So we end up with 1 plus c over e to the kt, and then we need to replace our u with what it was. U was 1 over y. So let's do that. 1 over y is equal to 1 plus c over e to the kt, and we want to solve for y. So to do that, I'm going to find a common denominator. We'd get e to the kt plus c over e to the kt. Then I'm going to flip both fractions. We'd get y is equal to e to the kt over e to the kt plus a c. And that should do it. I'm going to pause for a second because I want to go check that solution. I'll be right back. Okay, yes, this is the solution. This works. That's the solution. But also want to say it's common to see the solution presented in another way, and that if we were to multiply by e to the negative kt over e to the negative kt, then the numerator would be e to the kt minus kt. Denominator would be e to the kt minus kt plus c, e to the negative kt, and we end up with e to the 0 over e to the 0 plus c e to the negative kt, which in the end is 1 over 1 plus c e to the negative kt, and maybe that looks better. So to be clear, this works as a solution, and this one also works as a solution. Either one is just fine. That is the Bernoulli method, and we will go over that again some more on Friday, but maybe that helps you with your homework. And again, I'll post this on OneDrive. Okay, y'all take care, and I'll see you on Friday.